Okay, so today we're going to talk about hyperboloids of one sheet. So we have this equation here. This is an equation of a hyperboloid of one sheet. And as you can see, it has three variables, so x, y, and z. So a, b, c are just constants. So we have x, y, and z instead of just x and y because a hyperboloid of one sheet is plotted and graphed, also used in 3D coordinate systems, not 2D. So for 2D coordinate systems, we have parabolas, we have hyperbolas, etc. Right? We also have ellipse. So in the 3D coordinate system, we have hyperboloids of one sheet, two sheet, elliptical cones, etc. So this is an example of the graph of a hyperboloid of one sheet, and this is an example of the equation, or it's the format, the most basic format. There will be other varieties. So there are a few identities to our equation. So firstly, there are two positive terms. So terms with plus signs in front of them. You can add a plus sign there if you wanted, right? There are two plus sign terms, and then there's one negative term. We have one on the right hand side, so it's equal to 1, and then so we also have all three terms to be of degree 2. So degree 2, 3 times degree 2 terms. So these are a few properties of our hyperboloid one sheet equations. So now let's try and graph a hyperboloid, or let's learn how to graph a hyperboloid. So basically we have traces, so traces. And basically traces are a fast way to help us graph 3D equations by first graphing the 2D appearances of them at different angles and perspectives. So there are three traces. There's the XY trace. Basically we look down at the graph, so basically I graph what I think my hyperboloid of one sheet would look like if it intersected this XY plane over here. So the 2D shape, so it's obviously an ellipse because it's gonna be this shape here when it intersects my X and Y plane. So I graph that shape. And then we also have the XZ trace. So we have the XZ trace. Which is basically what I think my graph will look like if it intersects this plane here. So right now it's not really obvious, but it's actually I think it's a hyperbola. So basically a 2D version of what my graph would look like if it intersected. So if it intersected the XZ plane, and then the last trace you should obviously be able to guess is gonna be the YZ plane. So the YZ plane is basically what our graph looks like when this graph intersects the YZ plane, so this plane behind it. So the 2D version of the graph. It's also a hyperbola for a hyperboloid of one sheet. So for a hyperbola of one sheet, one of these traces are an ellipse, and the other two traces are hyperbolas. In fact, I forgot to mention something about the equation. So this negative term here with the negative sign in front is the axis which the graph would be parallel to. So it's parallel to the negative term, right? So now let's try to graph an example. So let's say I want to graph, let's come up with an example. X squared over 9 plus y squared over 16 minus z squared over 9 is 1. So that's an equation of a hyperboloid of one sheet. And in order to graph that, we graph the three traces first. So how do we graph the three traces? So for the first trace, xy, we just set z equals to 0. So if z equals to 0, z squared over 9 is 0. So we can just eliminate this term, and we get our 2D equation. So why do we actually set z equal to 0? Because if we want to see what the graph looks like when it intersects this plane, in this plane the z coordinate doesn't matter. There's no z coordinate. So namely the z coordinate is actually just 0. So this is the same logic for all the other traces, but firstly we just set z equals to 0, and we don't have this z term, so we can just have x squared over 9 plus y squared over 16 is equal to 1. And this is an ellipse, so it has minor focuses at 3, -3, major focuses at 4, -4. So this is an approximation of our graph here, something like that. So now we're going to graph the xz trace. So the xz trace is basically, so let me just highlight this equation. So the xz trace basically shows that, so basically we set y equals to 0 because when we're in the xz plane, the y coordinate doesn't matter, so it's just 0. So we have this equation here. Let me just write it. X squared over 9 minus z squared over 9 is 1. So in this case, we have a hyperbola, and this hyperbola here is basically something like this. And then we also have, so basically we also have the yz, so we also have the yz trace. So we just set x equals to 0, right? So we have y squared over 16 minus z squared over 9 is equal to 1. So these are our 3 equations for our traces. So that's also a hyperbola, and it's approximately, say, something like that. So now I have our 3 traces. We can just combine the graphs, the views, the top view, the side view, the front view, can call that, and then you can basically get like a graph of the hyperboloid of one sheet that you're desiring for. So we can just put the 3D coordinate plane here first. So this is x, so this is y, this is z, and the diagonal axis is x. So basically the top view here, the xy view, is gonna be of an ellipse. So it has coordinates of x is -3 and 3. Y coordinates -4 and 4. So this is our view from the bottom. So that's just approximately our top view. So our top view would be something like this. Or let me just use green to highlight this, emphasize this. So it's approximately an ellipse. If the bottom view is an ellipse, the top view is also approximately an ellipse, right? It's like from this shape. And then we also have the hyperbola. So we have a hyperbola on the x and z. So something like something like that. So to the other direction, you just can't see that. And then we have also the hyperbola to the z and y direction. So that's really obvious. So something like that. So we just connect, if we just connected these visualizations, we associated them with one another, we'd get a graph like this. So it's this green highlight, and all the points on the outside of this shape are part of the graph. So the points on the inside of the shape don't fit into the graph. They're not potential points that fit this condition here. So that's the example. That's an example of us graphing the hyperboloid of one sheet. So thanks for watching. Bye.